Hey guys, in this video we're going to be talking about numerical integration and in particular the trapezoid rule. This is from 4.6. So we're going to be estimating areas under a curve. Instead of using rectangles, we're going to break these into trapezoids. So one thing to note is that trapezoids, when you do this, they do not all have to be the same width. And that is true also for the rectangular approximation method. This is not all stuck together. So there are two ways to find the area of a trapezoid. If you do not recall the formula for finding the area of a trapezoid, write those down right now. You can use one or the other. You don't need to use both. But if you look at this picture over here, the blue graph, if we're finding the area under the blue graph and between that graph and the x-axis, the reason we would use this is if we don't have the equation and we just have some data in a table and you have to approximate the area under the curve. So we can break it into pieces and make a trapezoid, which is going to be pretty close to the exact area under the curve, but not quite. But any one of these, so I have, in this case, I broke it into, I have 5 different areas I'd have to add up, and I would plug in. These are your bases, so this would be like your base 1, base 2. So you take the average of the bases, which is what this is doing. You're adding the bases together and dividing by 2, so you're finding the average. And then the height is this direction, and you can kind of clearly see that A1, the width of that is, or the height for H in this equation, is smaller than it is for A3. So they don't have to be uniform width. But they can be, and it's more convenient if they actually are. So I'm going to do a couple of examples where a real-world use of this would be, and actually I have a friend who works for the state with hydrology. He's a hydrologist, and he goes out and he has to calculate like how much water is coming through a river to determine what the structural integrity of a bridge has to be, for example. And he's a hydrological engineer. So, and I've done this before with my classes, we can go out and measure across, and every so many feet, take a measurement of the depth of the water by just like, we take a tape measure, put it across, straight across like this, and every foot or so we'd measure with a meter stick to see how deep the water is. And then we take that data, create estimate the area of that, a cross-sectional area of that water by the trapezoid rule. So we don't have an actual equation for it. So let's do an example. Here's one. We're going to have non-uniform widths because this height is 1 foot, and this is going from 1 to 2.5, so it's 1.5 feet. First thing you'd want to do is tell whoever collected the data to next time to please keep it in even intervals. It makes it a little easier. But we're going to do this example. And so I made the diagram here a little bit smaller so that I can write it all out. Okay, so let's do this. We have the first trapezoid right here in red. I'll call it A1. That area is going to be, we're going to take the bases and add them together. This first base is 0.3 feet, and let's call them feet. And then the next base is 1.5. We divide by 2, and then multiply by the width or the height of the interval, which is 1 in this case. I don't really need the 1. And then we're going to add the next one. I'm going to show you some shortcuts as well in a minute here. But the bases for this is going to be, we have 1.5 plus the next base is 2. And we're going to divide that by 2 and multiply by this height, which is 1.5. So this is my second area. Oops. What I was going to do here is just do these all separately. So I have 1.5 plus 2 divided by 2 times 1.5. So that'd be my area for the second one there. The third one would be this purple. Oop, didn't change colors for me. The third trapezoid here will have an area of the bases will be 2, because I'm looking at the y coordinates, and 2.1. And it's going in the downward direction, but because we're looking for a cross-sectional, we're looking for the total area, we're going to make all of these positive. Alright, so we're dividing that by 2, and then the width of this interval goes from 2.5 to 3.5, so that is a height of 1. So why don't you guys go through, pause the video, and try to write out the areas for each of the remaining trapezoids, and then we're going to grab a calculator, plug it all in, and that'll be our total area. Okay, so I added up the different areas. We had 9 different trapezoids, all of different width, which makes it, like I said, a little bit more tedious. And so I ended up getting 16.17 square feet. If you did not get that answer, let me know. Maybe I made a mistake. I don't know. But hopefully you get the idea of how the process works. All right, so this is another problem. It's on averaging temperatures, and so the temperatures are taken from noon until midnight, and so we can change. Noon would be really correspond with 0, and midnight would correspond with 12. We're going to find the answer to this question. What was the average temperature for the 12-hour period? So average temperature is the average of all the y values, because the y values are giving me the temperature. So this is an average value problem. So what we need to do is find the area under the curve, and we're going to have to approximate it using trapezoids. And luckily in this case, it's going by every hour, so each of these, the height in each case, every single time, that height of that trapezoid is going to be 1. So that makes things easier, and I'll show you how we can work with that in a minute here. So what we need to do to find the average value, though, is find the area under the curve and then divide by the width of the interval, which is 12. And that'll give us the average height. All right, so I made this a little smaller here. So I have all these trapezoids, and so when I look at how to do this, the first trapezoid here, I'll call it A1. We're gonna look for a pattern here. I'm gonna put the 1/2 out front this time, and then the height. Well, no, the base for this first one, the base is 63. At noon it was 63, plus at 1 o'clock it was 65, and then I'm going to multiply by the height, which is 1. The second trapezoid here is going to look somewhat similar. We're going to have, here, let me write it out like this actually. I'm going to write the total area. So put AT for total. This is A1. And then so the second area, A2, I'm going to multiply, I'm going to have 1/2, and I'm going to add the bases again, and I have 65 plus the next base is 66 times 1. On all of these I can leave off the times 1, but if you write it, it's not wrong. So that's the second one, and the third one here is going to be 66 plus the next base, which is, the next temperature at 3 o'clock, which is 68, and I'm going to multiply by 1. So notice, every single time I'm multiplying by 1/2 and by 1, and when so I can factor out a 1/2 times 1, which is 1/2. So my total area, to take a shortcut here, we're going to factor out the 1/2, and we don't have to worry about that. If I pull a 1/2 out of each of these, then it's going to be 1/2 times parentheses. I'm going to have 63 plus 65 plus, then I have this half is pulled out, so I have plus 65 plus 66. The next one is going to be plus 66 plus 68. And so what we're going to end up with is because we're going to use the base, like for the next one, we'd have 68 plus 70. We can take a shortcut and double, like we can add 2 times each of these bases. Only the first base shows up only 1 time. So we don't do that for the first base, but this was That was for trapezoid number 4. And the next one will be 70 plus 69. So you can see that all of these values are going to continue like that. So I'm going to have 69 plus 68 plus, I have 68. So 69 plus 68 was for this trapezoid. Then I'm going to have 68 plus 68. And I have plus 68 again because it doubled up there, 68 degrees for 2 hours in a row, plus 65. So I have these two add together, these two, yep. And so, okay, so let's look at how this shortcut's going to work. What we can do is we can get an approximate total under the curve by taking 1/2 and then add up. We're going to have the first base plus 2 times the second base plus 2 times the third base plus 2 times, whoops, plus 2 times the next base, which is 68. Cut that off there. Plus 2 times the next base, which is 70. Yeah. Plus 2 times 69. And so this will make things a lot less tedious. Plus 2 times 68. Actually, I'm going to have 2 times 68 and 2 times 68 again. So if I want to really shorten that, I can go 4 times 68. Plus 2 times 65. Plus 2 times 64. Going through each of these bases. Plus 2 times 62. Plus 2 times 58. Plus, now the last one, however, is only going to show up once, just like the initial one did. So then I'm going to just go plus 55. I'm going to throw all that in my calculator. And that will be the area of the curve. And then I'll divide that by 12. All right, so what I got for a total was 782. And then to find the average temperature, divide that by the number of hours that we were working with, 12. And I get 65.17, which seems reasonable if you look at the data table. That seems like about an average temperature, where our lowest is 55, our high is 70, 65.17 seems reasonable. All right, that is it.